Hello everyone. What we're gonna look at in this video are examples from 5.7. I would like you all to read the examples in the book 7a, 7b, 7c, and don't worry about the formula over there. We'll just look at how to get the distribution of a function of a random variable just from scratch, okay? You have seen this kind of work done in example 1D from section 5.1, and also when we looked at if x is a normal random variable with parameters mu and sigma squared, then ax plus b is also normal and parameters are a mu plus b and a squared sigma squared. When we looked at the proof of this, that time we used the kind of techniques we're going to use in this section. Okay, so let's just take a look at some examples, a little different from what are in the book. All right, so here first, suppose that you have an exponential random variable with parameter lambda. It doesn't really matter what lambda is, so I'm just going to write lambda. And the random variable y is x squared. What you need to do is find the probability density function. I'm going to shorthand it as PDF of y. All right? Okay. So let's see. What we need to do over here, we know the PDF of x, we know the CDF of x, we know everything with x. We don't know we don't know the PDF of the CDF of y. So what we need to do to get the probability density function is go via the cumulative distribution function. So what do? First, look at the CDF of y. So what is the CDF of y? F sub y of y. That is the probability that the random variable y is less than or equal to y. Correct? Okay. So what do you know? You know that y is x squared. All right. So no matter what, y is never going to be negative. Okay. So you know that this is 0 if y is less than 0. The probability y is less than any number less than 0. So for example, if you put minus 0.1 here, when is y less than or equal to minus 0.1? Never. So the probability y less than or equal to any number less than 0 is 0. So it's good to put that out of the way first. Okay. And now what do we do when y is bigger than 0? Okay, so in that case, you have that this is the probability that x squared is less than or equal to y, right? Just replace y with x squared. Okay, so let's actually write it down all over here. So suppose that y is bigger than 0. The probability that y is less than or equal to y is the probability that x squared is less than or equal to y, which is the probability. Now let's take square roots here. And when you take a square root, you'll have a negative square root y less than or equal to x less than or equal to square root y. Okay? Now, what is x? X is an exponential random variable. What do you remember about an exponential random variable? Exponential random variable, do you remember what the PDF of an exponential random variable is? This is 0 to the left of 0, and it is lambda e to the minus lambda x to the right of 0. So the random variable x is not negative. So you can drop all the negative bits over here and just write this is equal to the probability that x is between 0 and square root y. Okay? And for that matter, you also do know that this is the same as the probability that x is less than or equal to square root y. We can even just drop the x between 0 and square root y, because when x is less than or equal to square root y, it'll always just be between 0 and square root y. X is never negative. Okay, now stare at this. And what is this? If you look at it, you know what this is in fact, it's the cumulative distribution function of x, where evaluated at square root y, right? Because you remember, what is f sub x of a? This is the probability that x is less than or equal to a. So if a is square root y, that's what you have exactly over here. Okay, so what do we have so far? We have that f sub y of y is f sub x of square root y. Okay, let's write that down. So f sub y of y is equal to f sub x of square root y. Okay, what did we want? We want to find the probability density function of y. So what do you need to do? You know that the probability density function is the derivative of the cumulative distribution function. Okay, so we want our hands on f sub y of y. You know what you need to do then is differentiate the cumulative distribution function of y. Okay, and since that equals this, we'll just differentiate the right hand side over here. Okay, so how do you differentiate this? You'll just have to use the chain rule. That subscript x over here has got nothing to do with the variable y. It's just telling you that's a CDF of the random variable x. Okay, you're just taking a derivative of this function, and you have to use the chain rule. Okay, so what do? You have to differentiate square root y, so y to the 1/2, so it's 1/2 y to the negative 1/2 times the derivative of this with respect to, just times the derivative of this evaluated at square root y. Okay, this is okay, so that is just exactly 1 over 2 square root y, and the derivative of the CDF of x is the PDF of x. And so you have that the probability density function of y is given by this. Okay, so let's actually write down explicitly what is it. So it's 1 over 2 square root y times the density of x evaluated at square root y. Okay, what is that? 1 over 2 square root y. Okay, and so you have that if y is bigger than 0, you have this. What is the density of x evaluated at square root y? Lambda e to the minus lambda x, but I mean you have f sub x of x is 0 if x is less than 0, and lambda e to the minus lambda x if x is bigger than 0. So we want to evaluate it at square root y, so we have a square root y over there. Okay, so you have that f sub y of y, actually the random variable y, that's the probability density function of y is, let me just write this in with more space. F sub y of y is this if y is bigger than 0, and it is 0 if y is less than or equal to 0. Okay, so there you go. You have it. This is the PDF of the random variable y, which is x squared, where x is exponential random variable. Okay, so let's quickly review what did we do. We looked at the random variable y. It is x squared. All right, and we want to find the probability density function of y. So how did we get our hands on that? First, look at the CDF of y. Okay, just by definition, this is just a definition. We looked at the CDF of y. That's the probability y less than or equal to y. Okay, we saw that 0 if y is negative, or let's just include the 0 over there. And it is probability x squared less than or equal to y if y is positive. All right, now we're going to look at that in detail Okay, so just suppose y is bigger than 0. We're looking at that part in detail. You have that f sub y is given by the probability x squared is less than or equal to y. Okay, well, what is that? That is the probability, it turns out, just parsing through this, is the probability that x is less than or equal to square root y, because x is always non-negative, which is just the CDF of x evaluated at square root y. Okay, so we have now an identity involving the CDF of y and the CDF of x. Okay, so you have a relation between CDF of y and CDF of x. Okay, what do you do then? Just differentiate both sides with respect to y to then get your relation between, that is the relation between PDF of y and PDF of x. Okay, right here. And then just write down what the PDF of x is, and instead of putting whatever variable you have here, evaluate it at square root y. Okay, and just make sure, it's very important that you very specifically find out when is the function 0, when is it non-zero, and so on. All right? Okay. So that was one example. And just so that this is absolutely clear, let's look at one more. All right, what we're going to look at is a random variable, y, which is a log normal random variable. What's a log normal random variable? A log normal random variable is 1. When you take the log, you get a normal random variable. So if y is log normal, what does that mean? When you take a log of y, you get a normal random variable. So what would that be? So you have x is a normal random variable. And let's say the parameters are mu and sigma squared. Y is log normal. Y is e to the x. Because now if you take a log of y, you do get normal. Okay, so we say y is log normal in this situation. All right, so let's find, or actually here, find the probability density function of y. Okay, so let's take a look at this. In the book, they have done this example, but they're just applying the theorem and the formula that they have in 7.1. You don't need to worry about the formula. What we want you to do is just be able to look at functions of random variables whose probability density function you know, and work through it just like we have done over here with that example, what we'll do in this current example, and also what you have in 7a, b, and c in the book. Okay? All right. So what's our first step when we want to find the PDF of a function of a random variable? The first step is find its cumulative distribution function. So that's what we're going to do. Okay? So y is e to the x. Okay? And what do you know about x? X is a normal random variable with parameters mu and sigma squared. So what's the range of x? That is from negative infinity to infinity, okay? And so if you have with e to the x, what's the range of y? That will be just from 0 to infinity, correct? Okay, so it's important to observe this because now we can see the probability f sub y of y, that's the CDF of y. That's the probability y less than or equal to little y. By definition, you know y is never less than 0. Or you will say that y is less than 0 with probability 0. So you put 0 if y is less than or equal to 0. Or even less than 0, it doesn't matter. And what do you have over here? This is the probability that e to the x is less than or equal to y bigger than 0. I mean, you could write that over there and that probability is 0. You could write the same thing over here and the probability is 0 for y less than or equal to 0. So I'm just very specifically ruling out what happens when y is less than or equal to 0, and we'll treat this more detailed case separately. Okay? All right, so we have that f sub y of y is equal to the probability e to the x is less than or equal to y. Okay, so let's take a look at that. So suppose that y is bigger than 0. F sub y of y is y less than or equal to y. That's the probability e to the x is less than or equal to y. X is random, e to the x is random. That's a random variable y. And now what do we want to do? We know stuff about x. So we're going to try and isolate x. How do we do that? We take log of both sides. Okay, I know previously I used log for the natural log. Over here I'm writing ln for the natural log. Really, I mean natural log, and it's quite clear which log I'm taking. Okay, so you have that the f sub y of y, that's the CDF of y, is the probability x less than or equal to log y. Okay, well, what is this? Stare at this. You know that this is f sub x, the CDF of x, evaluated at log y, right? So there you go. That's the first step. You want a relation between the CDF of x and the CDF of y. Okay, what do you do next? Now you will differentiate with respect to y, both sides. Okay, and what will this be? This is just the PDF. You get the PDF of y. What about this? Well, you have to use a chain rule. The derivative of log y is 1 over y. The derivative of capital F sub x is little f sub x. It's the PDF of x. And you want to evaluate that at log y. Okay, so there you go. The PDF of y is equal to 1 over y times the PDF of x evaluated at log y. Okay, so we're going to write down exactly what this is. First, let's remind ourselves what is the probability density function of a normal random variable. Okay, you remember what is this? This is 1 over square root 2 pi. I'll just write the y, sorry, not yx. X e raised to minus x minus mu whole squared over 2 sigma squared. Okay, and that's on the whole real line. All right, so that's the PDF of x, which is normal with mean mu and variance sigma squared. So we're just gonna, instead of evaluating at x, we're going to evaluate it at log y. Okay, so you have 1 over y. Oops, sorry, I made a mistake. This shouldn't be an x. That should be a sigma. 1 over y square root 2 pi sigma e raised to minus ln y minus mu whole squared divided by 2 sigma squared. Okay, and this is when y is bigger than 0, and you know that because f sub y of y is 0 if y is less than 0, you know that little f sub y of y is 0 if y is less than or equal to 0. Okay, so just writing this down neatly all together, you have the PDF of y that is 0 if y is less than or equal to 0. And it is 1 over square root 2 pi times sigma times y e raised to minus ln y minus mu whole squared over 2 sigma squared if y is bigger than 0. Okay, so there you go. And also it should give you a hint that there needs to be a restriction of where y is, because you have a log y here, and obviously you're not taking a log of a negative number. So you do need to make sure that you impose the appropriate restrictions of the domain of when it is this and when it is 0. All right. I hope that made sense. And I would say, well, this one's probably more complicated than the example 7ABC in the book. But I just wanted you all to have some extra examples to just make sure you understand all of these with someone explaining it to you. Okay, well, that's all for now. We have reached the end of chapter 5, and we'll have some problem sessions, collect all the examples or collect all the questions that you guys have, and we'll post a video with maybe answering them. So when you're going along looking at the homework problems, please write down what you can't do and email me and let me know what you can't do. Okay, all right. Take care and stay safe. All right, guys. Bye.